Jai Hind students, welcome to my YouTube channel. Students, always respect yourself. Do not feel sorry for yourself. Never ever feel sorry for yourself. Do not dwell on unkind things others may say about you. Polish and refine whatever talents the Lord has given you. Go forward in life with a twinkle in your eye and a smile on your face, but with great and strong purpose in your heart. So that should be the spirit. So students, with that note, let's start today's session. Today we are going to discuss the second episode of this unit of magnetism. In the previous lecture, what we have discussed was regarding artificial bar magnet, its properties, uses, isn't it? Today we will discuss some terms and definitions. Then we will be discussing Coulomb's law in magnetism, and in the process we will define the SI unit of pole strength. And then we will also discuss magnetic field and its mathematical expression. So let's start with some terms and definitions, right? So first and foremost, we will start with magnetic dipole. Dipole means having two poles. Now look students, as we have discussed, magnetic monopole do not exist. That is, magnetic poles always exist in equal and opposite pairs. So bar magnet, it's a fundamental arrangement comprising of two equal and opposite poles, that is north and south pole. So this fundamental arrangement comprising of two equal and opposite poles separated by a finite distance is known as a magnetic dipole. Actually, a bar magnet may be termed as a magnetic dipole, right? A current carrying loop whose one phase we have discussed behaves as north pole while the other phase behaves as south pole. So a current carrying loop behaves as a magnetic dipole. Actually, the electrons revolving around the nucleus inside an atom or molecule, it constitutes small current carrying loop. So all those behave as atomic dipoles, atomic magnetic dipoles, right? So magnetic dipole is nothing but a fundamental arrangement comprising of two equal and opposite poles separated by a finite distance. So bar magnet is a magnetic dipole, right? So this is the bar magnet, right? This is the bar magnet. And as we have discussed students about the poles of a magnet, poles, that is the magnetic poles, are not exactly the endpoints of a magnet. Magnetic poles are the preferred regions near the endpoints of a bar magnet, where the magnetic force of attraction is maximum. So it is near the endpoints of the bar magnet. So it can be considered to be the north pole, and this can be considered to be the south pole. Clear students? So these are known as the magnetic poles, and this is the fundamental arrangement comprising of two equal and opposite poles separated by a finite separation. So this fundamental arrangement is known as magnetic dipole. Clear students? This is, suppose O is the center of the length or the center of the dipole. This will act as the axis. This will act as the axis of the magnetic dipole. Axis, or it will act as the axial line. It will act as the axial line of magnetic dipole. And this right perpendicular bisector, that will be known as the equatorial line of the magnetic dipole. So students, magnetic length is the distance between the south and the north pole. So let us represent it by 2L. So this will be L from the center of the dipole, and the distance of the south pole from the center of the dipole would be also L. So, just as a convention, we will make use of 2L to denote the magnetic length. Clear, students? So, magnetic length is the distance between the two equal and opposite poles constituting a magnetic dipole. Point to be noted is that the magnetic length, that is 2L, it's a vector quantity. That is, it must possess both magnitude as well as direction. And its direction is from south to north. Please do remember this. We have discussed about the field lines. Field lines are in the form of continuous closed loop. Inside the body of the magnet, it's from south to north, and outside it is from north to south. So magnetic length is always directed from south to north, and it's a vector quantity. Obviously it's a length, its SI unit is meter. So that's magnetic length. And remember, students, this is the magnetic length, while the distance between the end points, the distance between the end points of a bar magnet is the geometrical length. And it is but obvious that the magnetic length is always less than that of the geometrical length of the bar magnet. Right? So, we are over with magnetic length as well. Now, magnetic moment. Magnetic moment of a bar magnet is defined as the product of magnitude of either of the pole strength and the distance between them. Now, students, as I have told you, these are the two poles having equal and opposite pole strengths. Suppose, let pole strength of north pole of the bar magnet be denoted by plus M. Right? Plus M, small m, it denotes the pole strength. Let us assume it. Then, pole strength of the south pole must be indicated by minus M. So, both the poles, south and north, are of equal pole strength, but different nature. So, its pole strength may be represented by plus M, and the pole strength, south one, it may be represented by minus M. So, both the poles are of equal strength in magnitude, but being opposite nature, one is assigned positive sign, the other one is assigned negative sign, right? So, magnetic moment, which is represented by capital letter M, is defined as the product of magnitude of either of the pole strength, that is small m, and the distance between them. The distance between the south and north pole, that is known as magnetic length, isn't it? So it is 2L. Now this is a vector quantity, magnetic length. So magnetic moment must be also a vector quantity. Again I repeat, students, the magnetic moment of a bar magnet is defined as the product of magnitude of either of the pole strength and the distance between them, which is obviously the magnetic length. Now, since magnetic length is a vector quantity, magnetic moment must also be a vector quantity. Magnetic length is directed from south to north. Therefore, magnetic moment must also be directed from south to north. So, this is the direction of the magnetic moment. That is from south to north. So what about its SI unit? The SI unit of pole strength is ampere meter. SI unit of pole strength is ampere meter, and SI unit of length is meter. So what do you get? Ampere meter square. This is the SI unit of magnetic moment. Here I must recall the magnetic moment of a current carrying loop. You must remember the magnetic moment of a current carrying loop is given by Ni. It is the ampere terms and the area of the loop under consideration. So SI unit will remain same. N is the number of turns, I is the current, whose unit would be ampere. Area, its SI unit is meter square. So ampere meter square, here also it should be same. But just remember, for a current carrying loop, the magnetic moment is given by the product of the ampere turns and the area of the loop under consideration. But while considering the magnetic moment of a bar magnet, the magnetic moment is given by the product of magnitude of either of the pole strength and the distance between them. It's a vector quantity directed from south to north. That is same as that of the direction of magnetic length. Clear? So this was about magnetic moment. Now students, after going through the definitions of these terms, that is magnetic dipole, magnetic length, magnetic moment, now we are in a position to discuss the next topic, which is Coulomb's law in magnetism. It is equivalent or synonymous to that of Coulomb's law in electrostatics. In electrostatics, we have considered 2 point static charges. In magnetism, we will consider 2 different poles, right? So, let's discuss Coulomb's law in magnetism. Coulomb's law in magnetism. So, let us consider 2 poles. Suppose its pole strength is M1 and there is another pole having pole strength of M2, right? And they are placed in air or vacuum at a distance of r. They are placed in air or vacuum. And students 1 and 2, these are the 2 long magnets, right? These are the 2 different magnets. That's why their pole strengths are different. Clear, students? So we have considered these to be long magnets because the other pole of this magnet will have no effect on this pole. So that's the condition why we have considered long magnets, so that only the force between these 2 poles can be studied, right? So M1, M2 are the pole strengths of the 2 poles of 2 different magnets. And the separation between them is R, and between them it is air or vacuum. So Coulomb's law states that the magnetic force between these 2 poles, and we are aware the nature may be either attractive or repulsive. In case both are north-north or south-south, then the nature of the magnetic force must be repulsive. And in case the poles are different, one is north, the other one is south pole, then the nature of the magnetic force will be attractive. So, Coulomb's law states that the magnitude of the magnetic force between the 2 poles is directly proportional to the product of magnitude of the pole strengths. Students, remember M1, M2, these are the pole strengths of the 2 poles under consideration. So the magnitude of the magnetic force is directly proportional to the product of the pole strengths, and it obeys inverse square law. Inverse square law means the magnetic force between these 2 poles is inversely proportional to the square of the distance between them. So again I repeat, students, Coulomb's law in magnetism states that the magnetic force between the 2 poles is directly proportional to the product of the pole strengths and inversely proportional to the square of the distance between the 2 poles. Clear? So if we combine these 2, what we get is F is proportional to M1, M2 divided by R square. Now we are aware, in order to eliminate this proportionality sign, we have to introduce some constant. So that constant is K. m1 m2 divided by r square. And in air or vacuum, the value of k, students, it is, we are already aware, it is mu naught divided by 4 pi. Mu naught, we are already aware, mu naught is absolute permeability. Absolute permeability of free space or vacuum. This we have already discussed. And its value is 4 pi into 10 raised to power minus 7. Its SI unit is Tesla meter per ampere. Tesla is the SI unit of magnetic field. Right? We have already done it in the previous unit. So students, the value of K in SI, it would be equal to, in place of mu naught, you can write 4 pi into 10 raised to power minus 7 divided by 4 pi. Therefore, K is 10 raised to power minus 7 Tesla meter per ampere. So do remember this value. So in case of air or vacuum, the mathematical expression would be F in air or vacuum. It is equal to mu naught by 4 pi m1, m2, m1, m2, these are the pole strengths of the two poles under consideration, divided by r square. R is the distance between the two poles under consideration. So this is the mathematical expression for the magnetic force existing between the two poles. And as I have told you, students, this magnetic force, it may be of attractive nature or repulsive nature, depending upon the nature of the poles. Like poles repel each other, unlike poles attract each other. Clear? So, with the help of this mathematical expression, we will try to define the SI unit of pole strength. SI unit of pole strength we have discussed, it is ampere meter. So let's try to define ampere meter. For this we will make use of this particular expression. So this is the mathematical form of Coulomb's law. So for two poles, two different poles having pole strengths m1 and m2 separated by distance r in air or vacuum, force it's given by mu naught over 4 pi. In place of mu naught over 4 pi, you can write as 10 raised to power minus 7 as well. m1 m2 divided by r square. So this is the mathematical form of Coulomb's law in magnetism. Let's make use of this expression so as to define the SI unit of pole strength, which is ampere meter. So what I'll do is, students, let m1 equals to m2 is equal to m, say. Let us consider both the poles under consideration are of equal strength. Each is equal to m. Also, let R is equal to 1 unit, in SI it will be 1 meter, and the magnitude of the force existing within these two equal poles be 10 raised to power minus 7 Newton. Let us assume these two. Then, if you substitute these values, what we get? In place of F, you can write 10 raised to minus 7. Mu naught over 4 pi, that is 10 raised to minus 7. m1, m2, each is m, so we'll get m square divided by r is taken to be 1, so 1 square. So we get m square is equal to 1, or m is equal to plus minus 1 ampere meter. So now we can easily define ampere meter with the help of these mathematical statements, right? Think over it, how to define 1 ampere meter when the pole strength of a magnet can be said to be 1 ampere meter. Can you try, students? It's pretty simple. You have to convert it into your own language. Okay. Let's proceed, right? Concentrate on the definition. The pole strength of a magnetic pole is said to be 1 ampere meter when it is placed at a distance of 1 meter in air or vacuum from another equal and similar pole. Experience or exert upon each other a force of 10 raised to power minus 7 Newton. Clear, students? Again I repeat, you have to include all these things, right? The pole strength of a given pole is said to be 1 ampere meter if it experiences a force of 10 raised to minus 7 Newton when placed at a distance of 1 meter in air or vacuum from another similar and equal pole. And obviously, as we discussed earlier, this force, it will be of repulsive nature if you consider equal and similar pole. This force will be of attractive nature if we consider equal and opposite poles. Clear? Again, I must repeat this statement, 1 ampere meter. The pole strength of a given pole is said to be 1 ampere meter when it experiences a force of 10 to the minus 7 Newton when this pole is placed at a distance of 1 meter in air or vacuum from another equal and similar pole. Clear? I hope you will be easily able to retain the definition of the SI unit of pole strength. Right? So, we are done with this topic as well. Now, let's proceed to the last topic, which is the magnetic field, and we'll try to find out an expression for the magnetic field. So, students, first, let's consider the qualitative study of magnetic field. Qualitative study. Now it's very similar to what we have studied in +1 during the concept of gravitational field, source mass, test mass. Similarly, in electrostatics, we have considered the qualitative definition of electric field by considering the concept of source charge, test charge, isn't it? So, qualitative study. Now, one thing to be noted is that magnetic field at a point is due to a source pole, right? And in order to detect the strength of the magnetic field at a point, we bring a test pole. It's just a hypothetical thing, it's an imaginary thing, but we need to understand the concept of source pole. We need to understand the concept of source pole, right? Suppose it is represented by M. Its pole strength is represented by M. And test pole. Its pole strength would be represented by M0. So magnetic field at a point is due to a source pole. Now what happens is, this is suppose a source pole. This is a source pole. Now look, it's a hypothetical study because isolated single monopole can't exist, isn't it? So we can consider it to be a pole of a long magnet. So in that case, we are considering this imaginary pole, right, which can be considered to be an isolated one. Now the source pole will modify its surrounding. It will tend to modify its surrounding. This may be considered to be its sphere of influence. So the source pole will tend to modify its surrounding in such a manner that if any test pole is brought near its vicinity, if a test pole is brought near its surroundings, near its sphere of influence, within its sphere of influence, then this test pole will experience a magnetic force. That magnetic force experienced by this test pole may be of attractive or repulsive nature. For convenience, if we consider it to be North Pole, this also to be North Pole, then obviously it will experience magnetic force of repulsion. Clear, students? So now we are in a position to define magnetic field qualitatively. Just as we have defined gravitational field, as we have defined electric field, in the similar fashion, we can define magnetic field. So students, magnetic field, it is the space property by virtue of which a source pole modifies its surroundings in such a manner that if when a test pole is brought near its surroundings or near its vicinity, then the test pole experiences a magnetic force. It may be either of attractive nature or repulsive nature, depending upon the nature of these two poles. So this space property is known as magnetic field. Clear? Now how to measure the strength of magnetic field at a point? Now what to do is, suppose at this point where we intend to find out the strength of magnetic field at this point due to this source charge, source pole, right? So the distance may be considered to be r, and it is air or vacuum. So we know that the magnetic force between these two, just now we have studied, is given by mu naught over 4 pi m1 m2. Here the pole strength of the source pole is m and the pole strength of the test pole is m naught, divided by the square of the distance between them, which is r square. We are aware of it. Now quantitatively or mathematically, magnetic field, it's a vector quantity obviously, it is defined as limit m naught tends to 0. This signifies the fact that this is a test pole. Its pole strength is negligibly small, infinitesimally small. Its pole strength can't be 0, but it approaches to 0. So why its pole strength is considered to be negligibly small? So that it do not alter the position of the source pole, and as a result of which the strength of magnetic field at a point can be found accurately, right? So it is defined as F vector divided by m naught. So this is the quantitative or mathematical study of magnetic field. So now students, concentrate on the qualitative or mathematical definition of magnetic field. Look, the magnetic field at a point due to the source pole is defined as the magnetic force experienced per unit test pole placed at that point. Clear, students? Again I repeat, the magnetic field at a point due to the source pole is defined as the magnetic force experienced per unit test pole placed at that point. Clear? So, if you substitute the value of F over here, what do you get? M naught get cancelled. So, we will be left with B is equal to, in magnitude, it will be equal to B equals to mu naught M. This is the pole strength of the source pole divided by 4 pi r square. So this is the expression for the magnetic field at a point which is at a distance r from the source pole. So this is the magnitude. And direction, students, we are aware. Direction of the magnetic field at a point is always away from the north pole and towards the south pole, right? Suppose it is north pole, it is plus. So magnetic field at a point will be in the outward direction. Suppose this is north pole of pole strength plus m. So at any point, the magnetic field due to this source pole would be directed outwards. And if this is a south pole of pole strength minus m, then at a point, the direction of the magnetic field would be given like this, towards the south. In this case, in the case of a south pole, the magnetic field will be directed towards the south pole, while